on plane stress, and we're going to talk a little bit about, or a lot of it about, in-plane principal stresses and maximum shear stresses. So what are we talking about in reality? We're going to talk about rotating the element such that we get to some maxima. Okay? So you can see max shear stress, it says max shear stress. Okay? But we're also going to talk about principal stresses. Right? And principal states of principal stress are when you have no shear stress. Okay? So it'll become a little more clear as we continue. Okay? Why do we care? We care because, as we've discussed kind of in passing, but not in real detail yet, some materials, the ductile materials, they fail because of shear stress. And then the brittle materials, they fail because of normal stresses. So if you get me to a state where I have only normal stresses, then I can figure out, okay, well, that, if it's a brittle material, then I have an idea of why it's going to, or how, if it's going to fail or not. And if you get me to a state where you have the maximum shear stresses, then, oh yeah, if it's a ductile material, I have an idea if it's going to fail or not. Okay? So, and there's some other things and quirks and whatnots, but that's kind of where we're headed with this. Okay? So, what are we trying to learn? We're going to learn what in-plane principal stresses are. We're going to learn what in-plane max shear stresses are. And we're going to calculate in-plane principal stresses while also being able to calculate in-plane max shear stresses. And the approaches outlined here are kind of, how do you say it, numerical, okay, in that you plot in Colab and then you pick points to figure out the answers, okay? We'll go through next time how you do this with a more graphical. I mean, this is graphical in the sense of, yes, you're plotting numbers and they are graphs. Okay, but next time we'll talk about a technique. It's, you know, just like you learned the unit circle, we're going to learn something called Morse circle, right, which is very helpful in being able to figure out equivalent stresses. So here we go again. We now have a set of equations for transformations. And they allow us to go from a state of stress with sigma x and sigma y and tau xy, so 2D planar stress, to a state of stress with a sigma x prime, sigma y prime, and a tau x prime y prime, like this. And, you know, we did the slicing, and we also have equations. And the equations are useful and help us go from one angle of rotation to another, right? So this is what we covered last time, right? And we just said, look, be careful. This is a theta here, which corresponds to this angle of rotation here. Okay, so nothing really new here. And you could look at it as, okay, this is the slicing of the triangle you need to do. But if I can solve for one angle of rotation, I can solve for many angles of rotation, okay, like this. So I can solve for many angles of rotation, whoops, and I begin to see that there are some local maxima, local minima, right? Local maxima, local minima, local minima, local maxima, right? So I can start to see that as I rotate by certain amounts, I get these states where maybe the normal stresses are maxing out. And look at this, even here. This is around 60 degrees for this particular problem, right? You see, this is 0 right there. Okay. Maybe it's a little less than 0, whatever, right? But you see this? at around 60 degrees, or maybe a little less or a little bit more, okay, this sigma x prime maxes out. And maybe this is more clear here, so it's a little less here, right? But this sigma y prime minis out, or minimizes out, okay? So we're starting to see that if we use these transformation equations, there's a state of stress that corresponds to 0 shear stress and maximum magnitudes, okay, of the normal stresses. Okay. And in-plane principal stresses are faces of element in a, okay, so principal faces, so, okay. Skip all the words. You get maximum normal stresses, okay, when you're in a state of principal stress. So this is rotating so that you get lots of normal stress. Okay. And this is in plane, all right, like this. So what we want to do is we want to find an orientation, right, or an angle of rotation that gives us this state of principal stresses, where we only have normal stresses, okay, and they are essentially maxing out. Okay, and that it kind of makes sense that if I get rid of one of my stresses, like the shear stresses, then the other two are going to be bigger, right? Or if I minimize one stress, it's got to go somewhere, right? That's so not physical speak, all right? And it does, I mean, ultimately, right, it comes down to these free body diagrams behaving in such a way that we see this behavior. Okay? But the state of principal stress is when you rotate and you only have normal stresses. 0 shear stress. Does that make sense? And we call that the state of principal stress, or we have principal stresses. Now, we put a very important word here, which will become more obvious in a little bit, not today, but in, I think on Tuesday, okay, it'll become more obvious. We're saying everything's in plane, in plane, in plane, okay, because we're only thinking in 2D. So if there was a question on the exam on Monday, it would be, okay, what is, it has to be kind of some in-plane, right? What is in-plane sigma x prime, all right? And then you do the whole, right, thing, all that stuff, slicing. Or you have the general set of transformation equations there, and you check to make sure that your slicing ends up being right. And you try to confuse me, making it look like you did the slicing, but really you just plugged in the transformations, and I am not patient enough to go through and make sure you did it. No. You get what my point is, right? So it's all about in plane. It's all about in plane in the membrane, okay? So here, there's an angle, and it's almost like an inverse problem, right? Before I was telling you, rotate this amount, tell me what you get for the stresses. Now it's, hey, what amount do you have to rotate to get to that state of stress, right? So it's like the backwards problem. So to do that, you can essentially plot the points like we said. So you do the collab, right? And you're like, hey, where does sigma x prime max out? Oh, boom. So I probably got to rotate like by 80 or something, or I could rotate by like 160. Okay, or 170, I guess, right? And rotate by 80, yeah, rotate by. You see this? I just need to plot one of these guys, sigma x prime or sigma y prime, and when I find a local minima or local maxima, or absolute actually in this case, all right, then I've got my number. What is the number I'm interested in? The angle of rotation. Now, when I get to that state of angle of rotation, if I do it by maxima on the normal stresses, then I got it. Or I can do it by looking at, okay, when does the shear stress go to 0? the shear stress going to 0 will also correspond to these maximum normal stresses. So these maximum normal stresses are what we call the principal stresses. Okay? So this is just drawing it out in more detail, okay? That they all line up with each other nicely, like this. And yeah, you know, they're going to be, the angle, right, they're going to be 90 degrees offset, the state of P1 and the state of P2. They're going to be 90 degrees offset. Essentially, just switch the X and the Y components. That's what you're doing. Okay, and here's Colab code, if you like, okay, to do this kind of thing. I'm going kind of fast because, once again, the time is nearly spent. Okay. So you can do this like that. This is 18.2. Okay. So part 2. Maximum shear stresses. Well, what do? You just look for the maximum shear stresses. Okay. Now, the issue with maximum shear stresses, okay, same problem we did before. Here, where are the maximum shear stresses? Maximum shear stresses maybe like at 30 or so, okay, and at like 100 and, I don't know, what's the, yeah, like 90 at whatever, 120, no, 100, yeah, 120 or so, right down there, okay, or maybe a little less, 124, so that's going to be like, maybe it's like, I don't know, it's maybe 20, 30, 34, something like that. Anyway, those maximum shear stresses do not necessarily have normal stress present. I'm sorry, when you're in a state of maximum shear stress, you're not guaranteed to have 0 normal stress. Okay? When you have maximum normal stresses, you are guaranteed to have 0 shear stress. Okay? But it doesn't work the other way around. So the state of maximum shear stress, okay, so this in-plane maximum shear stress can still have normal stresses present. Now, there are cases where you have no normal stresses. Torsion, right? The twisted bar or the twisted shaft, right? That's a case where we have pure shear. And so you have 0 normal stresses. Okay? But that's not necessarily a given. Okay? Is that clear? So that's different than the principal stresses. So once again, you can use Colab to find these. All right? And that's what I'm hoping you'll do with these exercises, is that you'll find out where these parameters are. And one thing here is that you'll see that, yes, there's 90 degrees, like we said, between one rotated state of principal stress to another state of principal stress. And that's just essentially flipping the X and the Y with each other. Okay? You'll see that you can go from one state of maximum in-plane shear stress to another with a 90-degree rotation. And then you'll see that you can go from maximum in-plane shear stress to principal stresses, maximum normal stresses, with a rotation of 45 degrees. So 45 degrees ends up being kind of interesting, and we'll talk more about that. Okay, but if you're in a state of maximum normal stresses, right, i.e. principal stresses, then you are going to be able to rotate that element by 45 degrees to get the state of maximum in-plane shear stress. Okay? And that's all we want to talk about. Well, that's pretty much it here. So the in-plane maximum shear stress, okay, does not necessarily have a state without normal stresses, but in pure shear with the twisting of a shaft, you do get that case. All right. There's a question there. Again, this is not due to Tuesday, so calculating in-plane principal stresses. So we can do the algebra, or the calculus, if you will, and you can go through this derivation. So instead of doing the graphical method, boom, here's an equation. It'll tell you. And here we begin to introduce another piece of or maybe already introduced it, but didn't describe it. Sigma 1, 2. When we flip, yes, we've talked about this, in pre-POMAX, we talked about sigma 1, 1, sigma 1, 2, sigma 1, 3. Well, in this realm, sigma 1 corresponds to the maximum normal stress. Sigma 2 corresponds to the corresponding normal stress that's 90 degrees off from it, and it's less. So sigma 1 we usually reserve for the largest principal stress, sigma 2 for the next largest, and we'll talk about sigma 3 in a little bit too. So that's how you can calculate them. And you can do a problem. You get to do a problem, okay? And then the maximum in-plane shear stress can also be done through some calculus, taking a derivative, and this is how you calculate the maximum shear stress through the equation. And this is what the normal stresses would be as well, right? Remember, maximum principal stresses, or principal stresses in plane, they're going to have zero shear stress. But you can get to your state of maximum in-plane shear stress and still have to carry some normal stresses along for the ride. Okay? But you can see here that if sigma x and sigma y are opposite of each other, this is foreshadowing, then you have maximum state of in-plane shear stress without any normal stresses, and that would correspond to pure shear, which is what you have in torsion. So if you are in torsion, if you have pure shear, and you go 45 degrees off from that, you rotate 45 degrees, you can actually get your state of principal stresses, and your state of principal stresses are going to have sigma x and sigma y with opposite signs. Okay, we will talk more about a lot of this stuff next week after the exam. This stuff is not on it, but hopefully what you've gotten out of the time that we spent together today is that the world does not care about our Cartesian coordinate system, okay? We have to adapt to the world, so we have to be able to think in terms of different rotations and transformations. Okay? Of course, we try to define the world in Cartesian coordinates that are easy and simple for us to use. Okay? And by doing that, then we are able to think about, okay, what amount of rotation is necessary to get to these states of stress that are critical for us to understand whether or not a structure is going to fail. Okay. Ultimately, the tools that we're introducing in this class are about, yes, analytical failure, so deciding whether or not something breaks, but hopefully, even before that, you do this type of work in the design process, and then you can make sure that your products that you're designing, whether they be bridges, whether they be toys, whatever they might be, rockets, Air Force, whatever they are, that they won't fail, right?